Okay, good morning. Are you guys happy this morning? Yeah, okay. So life is unpredictable, but there's always hope, right? What I'm going to do is that I know everyone had a really sad face on Friday noon, right? And so we have opportunity for you to make up some points. And this is the question that I'm going to ask you. I'm telling you now that I'm going to ask you this question just in a slightly different format because it's going to be online. All right, you got an email, you understand that. The problem I asked you on Friday was that there was a random variable x, which is uniform in the range of -1 and 1. And then I defined a new random variable called y. Y is 1 over 1 plus e to the power x, minus x. Okay? Now, you don't have to worry about this. It's just that y equals to g of x. Okay, some kind of g. And I asked you find the PDF of y. That's it. Okay? Now, of course, I'm not going to tell you the solution. Otherwise, that would defeat the purpose of your opportunity to strike back, right? So this is the problem. Nothing secret here. So if you want to study tonight, this is your last chance. Study this problem. Is this problem? The format is very simple. I created a grade scope exam, 30-minute online, fully online. No one is going to protect you. So if you want to cheat, I really cannot stop you. But please don't. 30-minute long for just this problem. Since we won't be able to grade anything, I just make a multiple choice. But it will be multiple choice of many, many steps. That the steps that you should have taken last Friday to solve this problem. Okay, the maximum number of points for this problem that you will see tomorrow, starting from midnight, this midnight, okay, 12 o'clock midnight, until tomorrow's midnight, 11:59 p.m. tomorrow. You have 24 hours to complete this 30-minute exam. The maximum number of points is 25 points. Okay, 25 points is 5 points fewer than the actual test because in this room, there are people who are really getting 30 points. So we don't want to penalize them too much. So it will be like 5 points less than those students. But anyway, so if you get, let's say you get 5 points on Friday, and tomorrow you really wake up, okay, you study hard, you get 27 points. Great, so I will give you 25 points. Okay, so you'll get a maximum 25 points. So that will replace your question 3 in the midterm. A fair game? I see a lot of happy face, okay? So opportunity is now given to you, and if you still mess up, that's not my fault anymore. It's okay? Okay, is this problem, please? Now, some of you ask, why are you so nice? Just because my personality. I think that the test has to serve the purpose of checking whether you have studied. If the test fails this purpose, then we need to rethink about the test and test you again to make sure that you have really understand the material. I don't mind teaching you how to do it, but I want to make sure that by the time you leave this room, you know how to do it because I think it is important. If it's useless, I'm not going to spend the time testing you. All right, so it is important. Please study this. Why it is important? Because in your career, you will eventually face this kind of problem. You're going to eventually face this transformation of a random variable because you want to deal with situations like that. That's the reason I'm emphasizing so much on this problem. Okay, the other problems, unfortunately, no more opportunity because multiple choice and true and false is there. The last problem is already many small little boxes, and I've done it in class on Wednesday. So I decided not to do it. But this problem, I really want to help you a little bit. Okay, so please study tonight. The window will open 12 o'clock this midnight, 24 hours until tomorrow midnight. Okay, 30 minutes and multiple choice. Clear? Okay, work hard. All right, so now it's not too early to start planning for the final exam. Final exam will be on a Wednesday. If I remember, it's on a Wednesday. It will be 2 hours long. Not in this room, I think. It's in another classroom somewhere. 2 hours long. The format will be similar. The format will be exactly the same as the previous year's exam. You have a few true and false, a few multiple choice, and 2 to 3 problems. I think it will be 3 problems because you have 2 hours. So the difficulty will be similar, the length will be similar, and everything will be similar. Okay. In terms of syllabus, I will decide towards maybe after the Thanksgiving, because I don't know how much we can cover this semester. If there are problems that I'm not going to test you, I'll tell you. So you don't have to worry that much. Okay, good. So for this lecture, what I want to do is to talk about something that I'm not going to test you in the exam. Okay, I want to spend some time talking about this because I think it is important. Now, as you are looking into your the next homework, so homework 6 or 7, you will start to work on a fairly big Python or MATLAB program. This program is about a classification problem. That will require you some knowledge about multiple random variables. In particular, we're going to use the concept of Gaussian, multidimensional Gaussian. So I want to cover that a little bit. So lecture 5.8, 9, and perhaps 10 will be more geared towards that, that project, sort of project and MATLAB programming. So what is it all about? I want to talk about random vector, but to motivate it, I want to start by showing you this problem. So you have an image, okay? You have an image. And in this image, there is a foreground. So you have a foreground. Okay, you have a foreground object. And then there are background. Background could be grasses. Okay, so that background. So this is your image. I will prepare you 2 training data sets. Training data set 1 and training data set 2. So this is foreground. This is background. Okay, so you have 2 data sets. I want you to train a classifier that can be used to classify pixels in this image and tell me whether this is a foreground or whether this is a background. Very practical problem. If you want to do machine learning, this is sort of the machine learning 101 problem that you must learn how to solve it. Okay, so why do I want to talk about this problem in this course, in this moment? It's because we already have all the tools to solve this problem. All right? So far what have we learned is discrete random variables and continuous random variables. In particular, we have learned Gaussian random variables. So and then you look at this problem, you say, wait, what is a random variable? What is a randomness here? So there are 2 things that I'm going to define. One is X, the other one is C. This is a pixel value. I'm going to change this a little bit later on. Okay, this is class label. Okay, so you can imagine that you have many pixels in this image. So these are all random variables. And then for each random variable, there's a class. There's a class. So what have we learned so far is that there will be some kind of distribution of the random variable. And it has to be class dependent. Class dependent means that if I'm in class 1, I will have one distribution. If I'm in class 2, I'm going to be in another distribution. So imagine this situation. Now, of course, this is purely hypothetical. You have class 1, and then you have class 2. Okay, 2 classes. And I'm just making things up. Okay, if you're class 1, you'll be a Gaussian. If you're in class 2, you'll be in another Gaussian. Now, you may debate with me whether this is truly Gaussian or not, given this image. We can talk about that later. But hypothetically, just assume that they're Gaussians. So how would you draw the distribution? Well, you have one Gaussian. You have another Gaussian. 2 Gaussians. Okay? Gaussian 1 and Gaussian 2. And they will have this distributions. F of x given C, well, you have some pixel value and then class label 1. You have f of x given C, pixel value given class C2. Right? So your class 1 and class 2, they are two different Gaussians. I need to learn these distributions, right? And I have training data sets. I need to find these distributions, which is something that we will learn. Now, how do we make the decision? How do we make a decision? Well, to make the decision, we also need another distribution, which is C. F of C1 and F of C2. Class of C1, class of C2. For example, you look at this image, there will be more pixels that belong to the background. So you will say, oh, if I randomly pick a pixel, even without looking at the pixel value, I think there's a high chance of getting the background. Just because background occupies more areas. Okay? So that could be some prior knowledge about the distribution. So you have these two. And I ask, OK, so now I give you a new testing sample. I say, hey, this is new x prime. OK, x prime. Should x prime belong to class C1 or class C2? Right, so this is a new testing point. So what I mean is that now I learned this conditional distribution from the data set, conditional from data set, prime from the data set, prime from the data set. I learned everything from data set. And then now I have a testing sample. Testing sample comes from this testing image. Okay? So I get this image, I pull out a sample here, and ask, hey, whether this pixel belongs to class 1 or class 2. So eventually what you will return me will be a binary mask, 1 or 0. 1 meaning that it is foreground, 0 meaning that it is a background. Right? 1 or 0. So how do you do this test? How do you do this test? Okay, how do we do this test? Any suggestion? You have this, and that. How do you do this test? You want to check something. Okay, so these 4 probability distributions. Yes. C given x. So let's think about that. So the suggestion is, let's consider probability of C given x. Class 1, x, in this case, it will be x prime. It will be a testing sample. Okay, x prime. Now, I want to compare it with something. And clearly, this x prime is given. So you have 2 x prime, cx. Okay, so this is class 1. This is class 2. The x prime is the sample, is the testing sample is given to you. It's the same testing sample for both sides. So you want to check which one is bigger. Okay? If this is bigger than that, what are you going to assign? Class C1 or class C2? You can assign the pixel to be foreground, background. What would you assign? If this is bigger than that, you assign it to be class C1 or class C2? C1, okay? If this is bigger than that, you assign it to be C1. The other way, you assign it to be C2. Okay, so class C1 and C2. So this problem boils down to if, okay, again, hypothetically, if I have access to this distribution, this is the flipped version of the distribution, then I can check whether this probability distribution, this value here will be higher than the other one. If yes, I will declare that the pixel will be C1. Otherwise, I will declare it as a C2. Okay, so what is the meaning of this distribution? This is, of course, a density function. Okay, it's a density function. The difference between this density function and this density function, one, is that this is the conditional probability of x prime given that you're in class 1. Here is the other way around. Suppose that I have already seen this pixel. It has a value of something, something, right? What is the probability that this pixel actually comes from class C1? So this is a forward reasoning. If I'm already class C1, what is the chance that I will get this pixel? This probability says if I am looking at this pixel value, what is the chance that it actually comes from class C1? So the two directions are different. One is forward, one is reverse. And the question we're asking here is reverse, because the problem given to you is that you're already looking at the image, you already have the pixel values. Now you ask, where does the class come from? Then, of course, you're asking this. Given the pixel value, what is the class label? Okay? So if this probability is higher than the other probability, certainly you would declare that this is C1. Otherwise, we declare it as C2. Okay, so now, why does it have anything to do with random vectors? Right? Nothing about vectors so far. So let's go back to this image. If x represents a pixel value, that would be a pretty bad idea, because the pixel value would just be a number between 0 to 255 for the 8-bit image. Okay? Now, in foreground, you will have some gray areas, and then in background, you will have some bright areas, but also some gray areas, some dark areas. So if you only look at the pixel, only a pixel, that's very not possible for you to differentiate whether it is the foreground or the background, right? Just think about if you look at an image, right? You will always have some gray areas, some brighter, some darker, but this brighter and darker will appear both in foreground and background. So how can you differentiate? So what we do in image processing computer vision is that we never consider just one pixel. We never, okay? When you have an image, when you have something, we always look at a local neighborhood. A local neighborhood. A neighborhood can be an A by A in our homework, A by A. So you look at this A by A, we call it a patch, a small patch, local neighborhood, A by A. Now this A by A can be useful because an A by A can contain an edge, and A by A can contain just the texture. And by looking at the edge and the texture, you can tell this belongs to the foreground, this is coming from the background. Right? So that will give you some information of deciding whether the pixel is foreground, background. So what you're going to do is that you look at a center pixel, you put a little small box around the center pixel, you grab an 8 by 8 or 9 by 9 or something. Okay? You put a box, and then you grab all these pixel values in this box, and then you do this analysis again. But if you want to do this analysis, then it is no longer just a pixel value, but an array of pixel values. Okay? So I'm going to replace this by a underscore that defines a vector. Okay? It is an array, but I can always convert it to a vector. It would be, if this is A by A, this is equivalent to a 64 by 1 vector, just the same number of elements. So this is a vector x prime, where x prime would be a vector in your image. This x will just be the random variable denoting the vectors. Okay, so what you're going to do is that you look at this image, you look at this pixel, you put a box, you look at this pixel, you put a box, move around, and you make this decision, sort of loop through it. Okay, it will take some time on this Python MATLAB programming, but that's all right. We're not doing this model deployment in Facebook, so we don't have to be real time. Okay, so it's okay to be slow. So you do this loop through all the pixels one by one. For every pixel, you put a box, and then you check this condition. If this is true, you put a 1. Otherwise, you put a 0. So keep going, and then you will be able to find out whether this is foreground or background. Not perfect, but in this problem, you will get a pretty good result, because I manipulated the image in the training set so that you will get some happy results. If you only go online, download some images, prepare your own foreground and background data set, it's not going to work. because the model that we are using is just too simple. Now, to detour a little bit, neural networks today is doing something very similar. Neural networks today is doing something extremely similar. If you ever know something about neural networks, they're pretty big. They're pretty big. You have multiple layers of networks, neurons. The final layer is a very simple linear regression decision rule. It's a linear decision rule. So you can imagine that you spend most of the time in a network. So let's say you put an image in. Okay, so this image in, and then you start to pull features. Okay, so this is like a drawing of the neural network. So start to pull features, so it's like a funneling. And then ultimately, you will trim it down to a very small vector. And when you do this vector, you're going to do this classification, very simple classification based on this vector. So what we are doing is that we of course, we don't have a network. We're not pulling any feature. We're really lazy. We say that, OK, this vector is just a concatenation of these pixel values. Right? In network, why networks are so powerful? Because they have all these layers. Every layer, they're pulling some feature. High level, low level, mid level features. And at the end of the day, these are the, you can imagine this is like a black box. So this is image, and then it is giving you a code, a secret code. This code is sort of describing what is happening in the image. And so you need a lot of layers to turn it into this code. And then once you have this code, you just do the linear classifier, which is what we're doing here. Okay. Modern neural networks, of course, will do something really, really fancy. Okay. Dilated neighborhood, transformers, what else can you name? Okay. Gated attention, you have a lot of these crazy things. It's all about getting the features. Okay? Residue network, convolution, anti-convolution, different kinds of networks, they're all here to pull the code. So if you understand what we're doing here, you will be maybe understand a little bit better about what is going on in neural network. Okay, so let's go back to our discussion. Now we have all these little patches, and then we have all these vectors. Okay, so each hx is no longer a scalar random variable, but they are a vector of variables. Okay, so you have a lot of numbers in this vector. How do we describe the distribution of this vector? If I would say, hey, this is a Gaussian, one-dimensional Gaussian for one random variable, now it becomes a vector of Gaussian random variables. How do they look like? So this is the purpose of this 5.8. Okay, lecture 5.8, random vector, and also 5.9 to talk about some properties of a Gaussian. So I will go through this set of slides very quickly because I'm not going to test you. I will just tell you some notations so that you can work on your homework problem. So that's the purpose. More than two random variables, the joint distribution is just a high-dimensional PDF. The way to think about it is that you go from one random variable to joint distributions. So you have a pair of random variables, so fx1, x2. Now, easily, you can make it into 3 variables. You can into n variables. So you just have a lot of random variables. And now, if I'm lazy, I will just call it fx. Now, on paper, computer can type it as the bold vector. If I write it using my pen, I will just put an underscore to denote that this is a vector. Okay? A vector will contain n elements. So you have n random variables in this array, and then you have n states coming together. The way you think about this can be generalized to this situation. So here you have a two-dimensional plane. You have pulses, or there's a surface. So that would describe the density of having this pair of states, x1 and x2. So here you will have a n tuple. I cannot draw it, but you can imagine that there will be a delta function, a height located at this coordinate with n numbers. So that's the picture of a high-dimensional distribution. We study high-dimensional distribution because all images here, let's say a crop a patch, you have n pixels, is already in this really crazy manifold. That's just the nature of the problem, so we want to understand that. So what is a random vector? A random vector is a vector that contains many, many random variables. So here is the vector x. Here is the vector of states, small x. And so the joint PDF will be given by this high-dimensional function. Now, don't worry, I'm not going to ask you to integrate anything, because if you mess up in integrating two random variables, how can I trust you to integrate n random variables? So I'm not going to ask you to integrate n random variables, but I'm going to tell you a trick. How do we deal with these all the time? In general, if this is a joint distribution, and if you want to integrate over an area called A, okay, then you have no choice. You need to do this multidimensional integration. It's really, really messy. But in most of the situations, your pixels can be independent. Not always. Not always. Okay? But in some situations, they are independent. Now, if they're independent, then life is very easy. If they're independent, then your joint distribution can be factorized into a product of n individual distributions. And assuming that they're all identically distributed, then you just have this f repeated n times. And so the time that you want to calculate this integration, originally you need to integrate this n-dimensional integral, which is an extremely messy thing. You can just cut it down to the individual probabilities. Okay, just calculate one and then take it to the power n times. So that will make your life a lot easier if they're independent. And we're going to explore this independence a lot in our calculation. When you have a random vector, we can talk about the mean vector. The mean vector will just be the expected value on this random vector. And so you have n elements, or n expected values. Just do it in this way. Just to write it out, you have n integrations. Each one will be the single variable integration. You have all these n individual distributions. So here is an example. If you're a Poisson, for each xn, they're independent Poissons, and they have a different mean. Then you just calculate each one individually. So if I say x is a Poisson of lambda vector, then the expected value of this x would just be lambda 1, lambda 2, to lambda n. Right? Because the mean of one Poisson is lambda, and so the mean of all these individual Poissons would just be individual lambdas. So that's pretty easy. Now, this one will take us some time to learn. It is called a covariance matrix, okay? Especially for Gaussian. Covariance matrix, it is an n by n matrix. You have n columns and n rows. The diagonal elements of this covariance matrix, they are the variance of the individual random variables, x1 through xn. And then the cross terms, they are the covariance of the xi and xj. So you can imagine that if I have two random variables, x1 and x2, then my covariance matrix x, this I put a vector here to denote this as a covariance of this vector x, which contains two elements. Then it will be variance of x1, variance of x2, and then here will be covariance of x1, x2, and then covariance of x1, x2. These two has to be the same because covariance of x1, x2, and x2, x1, they're the same. So you have a symmetric matrix. Okay, symmetric matrix. This half will be the same as the lower half. The covariance matrix can also be defined according to this formula. It is your random vector x minus your mean vector mu, and then you take this outer product, x minus mu transpose. So here you will have a x minus mu will be a column vector. This x minus mu transpose will be a row vector. Then when you take this outer product, you will get a matrix. So this is the meaning of the covariance matrix. Any high-dimensional distribution will have a covariance matrix. Whether it is a Gaussian or not, you will always have a covariance matrix. The covariance matrix is important because it tells you how correlated is one variable to another variable. So if you think about the patch here, it is quite impossible to assume that all the pixels are independent, right? It is very, very likely that they're correlated in some ways. So we should expect that in this problem, there will be a covariance matrix for the 64-dimensional vector. We need to calculate that. In the special case where your vectors, they're all independent, then of course your covariance terms will become 0. So you will return this very simple, just a pure diagonal matrix with the variance. So that would be your covariance matrix. So that's a special case. There is a thing called a correlation matrix, which we don't really need that for now, but I will just state that the correlation matrix will just be the joint expectation. The covariance, you need to subtract the mean. All right, so here is the deal. You have this multivariate Gaussian. Okay. In our programming problem, we are going to assume that given the class, when you look at the patch, it will be a Gaussian distribution. It will be a high-dimensional Gaussian distribution. A high-dimensional Gaussian distribution has to be defined by this formula. It looks pretty ugly, but if you understand what is going on in the single variable Gaussian, you should be able to understand what's going on here. In a single variable Gaussian, you have 1 over root 2 pi sigma square e to the power minus x minus mu squared divided by 2 sigma square. So this is a single variable Gaussian. Now, as you are extending the dimensionality from one dimension to multiple dimensions, your vector, of course, your x will become a vector, a scalar becomes a vector, your mean will become a vector. Now, there is a term here. This is the sigma inverse. Sigma is the covariance matrix of your vector. So covariance inverse, think about the special case. This is your sigma. If you only have one variable, then sigma will just become the variance of x if n is 1, right? So that will return you the variance, which is sigma square. Think about the special case. So now when you put the sigma inverse, it will just be the sigma inverse, sigma square inverse. So here, that sort of explains the presence of this term, okay? Matrix inverse. And then you have this sigma determinant. So the determinant is the matrix determinant. We don't have to know how to calculate that. Nowadays on Python, MATLAB, just type determinant. You can calculate the determinant. It's not a linear algebra course, so I'm not going to test you how to do this. But there's a term you can calculate. There is a power d here. D is the dimensionality of your vector. So if your vector x is x1, x2, all the way through xd, then d will be here. So d, in our problem, d will be 64. 64-dimensional vector, so you have d 64. Now, why do you have this d here? This d is that you think about the independent case. You just multiply the single Gaussian 64 times. That will give you this 2 pi to the power d. That d will show up. Now, if you are correlated, the d will still be there, just because you have 64 times your 64-dimensional vector. Okay, so this is the notation. Now, in Python and MATLAB, it's fairly easy to type. You just type 1 over square root 2 pi to the power d times determinant np dot determinant times the np dot exp exponential, right? Minus 1/2 np dot product, and then you input your inverse. So np's inverse. Okay, just type those kind of things into your program. You can calculate that. So that's not hard. Okay? So you can do that. Now, what does the shape look like? The shape of a Gaussian looks like this. Here are the three choices of your mean and your covariance matrix. Okay? Mean and covariance matrix. Let's look at them one by one, okay, to get some ideas. This is a two-dimensional case. You have a mean of 0, 2. 0, 2. Where is the 0, 2? Well, your first variables is 0, so it's here, right? 0. This is 0, okay? And then your second variable is 2, 2. So therefore, your Gaussian is centered here. If you look at 1, 2, 1 and 2, your Gaussian is centered here. You look at 0, 0, 0, 0, your Gaussian is here. So that determines where your Gaussian is centered. So that's the mean vector. Now let's look at this. This, you don't have any zeros on these two off diagonals. You only have 5 and 0.5. And let's look at this, your width and your height. Okay? So you have 5, more or less 5, and 0.5. You got that? Okay? So this will tell you sort of the spread along the two axes. Right? You get that? So the mean will tell you where you are located, and then the covariance matrix will tell you the shape. And then now the two diagonal elements will tell you the length of the major axis and the minor axis. How about the off diagonals? The off diagonals is going to tell you the orientation. Whether you are rotating 45 degrees, 35 degrees, or 90 degrees, or something like that. So that is the meaning of these two. Now, to convert a covariance matrix to this angle will require some work. So that's not trivial. But I'm just telling you that the diagonal will tell you the magnitude, and then the off diagonal will tell you sort of the angle. You should think in this way. So if I have a 64-dimensional covariance matrix in your problem, you should imagine that the mean vector will tell you where the Gaussian is located, and then there's a high-dimensional Gaussian, the quote-unquote orientation, which is defined by the covariance matrix. So when you have two classes, class 1 and class 2, okay, class 1 and class 2, the decision boundary that you're making is based on the rule that we're deciding here. The rule says that, okay, I have a testing point x prime. Whether this is closer to this or is it closer to that. And so what it means is that I'm going to calculate if I come from this class, what is the probability? If I come from this class, what is the probability? So you do this kind of checking. The decision boundary of our problem is not a straight line. It's a little bit more fancier. It is going to be a curved decision space because we have a different mean vector, we have a different covariance matrix. If you have the same, covariance matrix, but then different mean vectors, then you're guaranteed to get a linear classifier straight line. But in our problem here, it's like a quadratic classifier. It's a little bit more fancier than the linear case. Okay, so anyway, this is a summary. But before I go to the next set of slides, I want to comment on one question. one very important question, which is going back to this problem here. You have image. This is a testing image. This is training data set. Training data sets in your problem, they are stored as the docx file. So you can download the docx file. The docx file, they are organized into, I forget whether this is based on row or column. Anyway, if it is row, you will have each row will represent a training sample. Each row will be 64 dimensional. Is it okay? So in this data set, it will be, I don't know, okay, I really forgot whether I put it into row or column. If it is a row, then you will have 64 dimensional vectors. So each row will be one training sample. Okay, one training sample. Each training sample means a patch. A patch somewhere, I gathered somewhere. Okay, don't ask me where I gathered it, but gathered somewhere. And then you have many training samples. So here you have, I call it class 1, so K1. So this is class 1. So K1 number of samples. Maybe there are 9,000 samples. I don't know. I forget the number. Now, and then now you have class 2. You have the same format, 64, and then here you will have K2, maybe 3,000 samples. I don't know. Okay, so there are two different numbers. So given these two gigantic training data sets, what do I need to do in terms of training? Okay, what do I need to do in terms of training? Well, I want to calculate what? I want to calculate this, x vector in class 1. Okay, I want to calculate this. And I tell you that it is a high-dimensional Gaussian. That means it is a Gaussian of some vector given class mu1 and then sigma 1. Okay, every Gaussian is specified by the mean vector and then the covariance matrix. If I tell you the mean vector, I tell you the covariance matrix, you will be able to define this Gaussian distribution. It's parameter family. So what should I do here? Well, I need to find out the mean vector and also the covariance matrix for my class 1 Gaussian. And now you're given this data set, class 1 data set. How do you find the mean vector? How do you find the covariance matrix from this mean vector, from this data set? How do you do that? Any suggestion? The data is arranged in this format. K1 rows, okay, K rows and 64 columns. I just want to find out the mean vector. Mean vector, yes. Exactly, so he can graduate now. See, don't overthink. You want to calculate the mean vector. You have k vectors. Just take the average of these k vectors, you get a mean vector. That's your mean. Okay? How do you get a covariance matrix? You want to try it again? Oh, you want to try it? Okay. Uh-huh. 99% correct. One keyword is missing. It's called the outer product. Outer product, because you want to do this x minus mu and then x minus mu transpose. Right? Okay? And then you have n of those. Just do this n times, and then sum them up, divide by n, boom, you get the covariance matrix. As simple as this. Okay? And if you are talking to a lazy person like me, I would tell you in MATLAB is mean. MEAN of x. Done. The other one will be COV, covariance of this matrix. Now you need to do a little bit of debugging to make sure that you're using the right syntax, you're inputting the right format, because I really forget whether MATLAB or Python wants to take this format or the rotated format. Whether they want each sample to be organized in a row or they want it to be organized in a column. I forget that format. So please check to make sure that your mean vector has to be a 64 by 1 vector. Okay? Your covariance matrix has to be a 64 by 64 covariance matrix. If you type a command and it runs out of memory or your computer freezes, that means you're doing the wrong thing. If you're doing the right thing, it should be boop, it should come up immediately. Okay, so this is how you can get the mean vector and also the covariance matrix. You repeat this process for both class C1 and class C2, you're done with the training. Okay, now you will be very surprised. I thought in machine learning training is going to take a couple hours. Not necessarily. This is the good old days machine learning before we have the deep neural network. So this training is done instantly by reading the data sets and then come up with this parametric model. So it's done right there. The testing will take some time because you need to look through each pixel individually. Okay. Now, today's deep neural network will take some time to train because the data set is a lot bigger. Also, the model is a lot more complicated. You don't have this parametric family. And so when they're trying to search for these neuron weights and also the bias and so on, they need to solve an optimization problem. So those will go to stochastic gradient descent and stuff like that. That would take forever to converge. But for simple problems like ours, it will be instantaneous. Okay? So during testing, what you should do is that you go back to the formula, go back to here, just check this, and then you should be good to go. In your homework assignment, I divided the programming into 2 consecutive assignments. Part 1 would be for the current homework assignment that you will be asked to read the data, manipulate the data a little bit, and then do the training. Part 2, which would be the next assignment, you'll be asked to write this double for loop, loop through the patches, and then grab the patches, and then do this testing one by one and report me the binary mask. Okay? Now, the last 2 minutes, I would just want to comment on, please do not use this training data set to do any other problems because it will fail. Okay? It's not about the copyright problem. It's about that it just doesn't work. Why? Because in order to make you feel happy, feel some success of working on this problem, these 2 data sets, they're cheated. Okay? They are taken from the image with the ground truth label. And therefore, it works only for this image. Okay? But that's sort of the educational purpose. If I really give you some generic data sets, then you need to do a lot of engineering, pre-processing, image processing to make it work for this image. And that defeats the purpose of learning this probabilistic reasoning. Okay? You're going to spend 99 hours on manipulating the data and just 1 hour on this. That's not the purpose. So I want you to really understand this principle. Now, if you take this data set and test on similar pictures online, you fail. That's the reason. Because the data set, the training data set has been so biased to this image that it only works for this image. And in machine learning, we call it as a huge domain gap. All right, so don't complain that. So that's the comment here. Now, if you work on this problem, you find it interesting, then a challenge for you would be to open problem, no credit. We can chat offline. Now, if you want to improve the detection rate, what are you going to do? Okay, if you have these are the general data sets. What should you do to make it more robust to handle images like these? So we can talk about these offline. Okay? So I hope this motivates you to work on a little bit on this problem, start early. And I find it really interesting for this problem. Once you understand this problem, then you really understand the conditional probability, the prime probability, and also the posterior, Bayes theorem, and all these kind of things, they will merge together. So work on this. And don't forget a gift for this midnight. All right? So I will see you on Wednesday.